Today's lecture concerns the random effect method of estimation as well as the Hausman test. Now this lecture continues our series of lectures on the linear unobserved effects model for panel data, where last time we talked about two different methods for estimation known as fixed effects and first differences. The random effects method constitutes a different approach which relies on slightly different assumptions. So the outline for this lecture goes as follows. We'll talk about random effects in details, starting with identifying assumptions, which will lead us into a discussion of the structure of the error variance, which will suggest the random effects estimator. We'll see that random effects amounts to something like time to meaning, known as quasi time to meaning, and then we'll talk about how to implement this estimator in practice, as well as how to estimate its asymptotic variance and therefore do inference with the estimator. Towards the end of the talk, we'll then talk about the Hausman test for comparing the random effects and fixed effects approaches. Starting with random effects methods, let's talk about identifying assumptions. Now, our first identifying assumption is assumption RE1, or the first random effects assumption. In this assumption is built up of two parts, where the first assumption is that the idiosyncratic errors conditioning on the regressors in all time periods, as well as the individual effect, that they have conditional mean 0. The second part states that the individual effect itself, conditioning on regressors in all periods, has conditional mean 0 as well. Note here that the first part is simply our assumption of strict exogeneity, or what we would call FE or FD1. So the first part of the random effects assumption, it not only implies that the individual effect and idiosyncratic errors are uncorrelated, or that the regressors and the idiosyncratic errors are uncorrelated, it implies strict exogeneity, or rather it maintains strict exogeneity. So it's only the second part of this assumption that's new to us. Now the second part of this assumption, RE1b, imposes that the individual effect is mean independent of the regressors. So that was the first equality up here. That's new to us, and it may or may not be restrictive in practice, depending on the type of interpretation we will give to the individual effect. Note that we're not only imposing mean independence, but also in fact a zero conditional mean. However, the zero mean is not, well, given the conditional mean independence, first equality, the assumption of a zero mean of the individual effect can be enforced by simply including an intercept among the regressors, which is not that restrictive. So henceforth, we'll assume that the regressors contain an intercept term. Now, since the second part of the random effect, the first random effects assumption, is new to us, it is precisely this feature that distinguishes random effects from fixed effects. Note that taken together, the first random effects assumption implies that the composite errors, what we may call the VITs, that is the sum of the individual effect and idiosyncratic errors, it implies that the composite errors are uncorrelated with the regressors. This is much more restrictive than what is actually needed for pooled OLS, which were precisely these two conditions up here, amounting to uncorrelatedness. Hence, under these assumptions, we may do pooled OLS, but we may also be willing to do something else That is, if we believe in this assumption, we may be willing to impose additional assumptions in an attempt to achieve a more efficient estimator. Now, of course, the first random effects assumption is not sufficient for identification alone. We also need some version of a rank condition. In order to, before we state this condition, it'll be helpful to stack the composite errors, the VITs, into a vector. Let's call it boldface V, which is then a t/1 vector. Now, under the first random effects assumption, the composite errors have zero mean, and so this vector is a zero mean vector. Hence, if we take the expectation of its outer product, which is what will appear down here, we get its variance. Now let's just, for the sake of simplicity or notational simplicity, let's denote this composite error variance by omega. And note here that omega is then a t/t matrix. Now the rank condition here then goes as follows. Namely, if we look at the expectation of the regressors, which, let me remind you, when we write boldface xi, we mean the t/k matrix arising from stacking the xi(t)s over time. So we're considering this matrix, which is again a sandwich or a quadratic form constituted by the regressors and the inverse of the composite error variance. We're assuming that in expectation this matrix has full rank. Now in interpreting this assumption here, it may be helpful to just ignore this inverse, in which case this assumption just amounts to a full rank condition, very similar to the rank condition imposed in, say, the cross-sectional model or linear model with cross-sectional data. Now, since the regressors that we are now dealing with here are t/k, this matrix, and therefore its expectation, is a k/k matrix, and full rank amounts to having a rank of k. Note here that since we're not doing any differencing or time demeaning or whatnot to our regressors, this rank condition actually allows for time invariant regressors, which is precisely why we can include an intercept among the regressors. This is in contrast to our latest lecture where we discussed the fixed effects and first differencing ideas, which would wash out time invariant regressors. Let's proceed to discussing the error variance structure or error structure. Now, at this point, we could actually proceed by using given the assumptions that we've made thus far, we could proceed with a generalized least squares approach to estimation, or rather a feasible version thereof, or FGLS. The resulting estimator would be consistent, at least under mild additional conditions. The idea here of the generalized least squares approach, or GLS approach, or its feasible version, is to stack the observations over time for a given individual, thus creating a linear system of t/1 equations. Now here I've collected the error components into the vector vi, or I've explicitly written out the vector vi as the sum of two parts. One is a vector of the individual effects, which don't vary over time. So recall that this jt is our notation for a t/1 vector of ones. And the boldface UI simply stacks the idiosyncratic errors over time for a given individual. Now, given this linear system, we could go ahead and apply general results for OLS, which would result in an estimator known as system OLS. Now, the details for the properties for such an estimator are given in Wooldridge's chapter 7, which we won't cover explicitly since it won't be needed for our purposes. Now, we could proceed with an FGLS approach given this linear system and the assumptions made thus far, but we wouldn't really be fully exploiting the composite error structure given by the panel data. Now, what's known as a standard random effects analysis will further restrict the form of the composite error variance matrix, and that's what we'll do next. Now, our third random effects assumption is also given in two parts. The first part states that the error variance, or rather the idiosyncratic error variance, conditioning on regressors in all time periods, as well as the individual effect. This error variance is a scalar matrix. That is, it is proportional to the identity matrix, which here is t-dimensional, up to some proportionality factor, which we'll denote by sigma square u, representing the variance of the idiosyncratic errors. The second part states that the individual effect, its conditional variance, conditioning on regressors in all time periods, is constant. That is, it doesn't depend on the regressors. Now, the first part of this assumption, RE3A, implies that the idiosyncratic errors are homoscedastic and serially uncorrelated, both in a conditional and an unconditional sense. Hence, their variance doesn't depend on t itself, nor does it depend on the regressors in any time periods or the individual effect. Also, the idiosyncratic errors are uncorrelated over time. The second part is an assumption which we should be comfortable with from the cross-sectional case, in that it simply implies that the individual effect is conditionally homoscedastic. Its variance does not depend on the regressors. Combined with the first random effects assumption, this third random effects assumption implies that the conditional error variance of the composite error term, where we conditioned on xi, doesn't depend on the conditioning variable. That is, the conditional composite error variance is independent of xi, or the regressors. Hence, it reduces to the unconditional composite error variance, which is what we called omega. So let's take a closer look at omega under these assumptions, that is, under the first and third random effects assumptions. Under these assumptions, we can expand on omega to see that on the diagonal, it's given by the sum of the variances of each of the variance components. That is, the sum of the variance of the individual effect and the variance of the idiosyncratic errors. Now, off diagonal, it is all of these. Off diagonal, it's given by the variance of the idiosyncratic, or rather the individual effect. One may see this by looking at the expectation of the product of composite errors, which writing out would be the product of, or the expectation of this product. Now, expanding, we get the expectation of the square of the individual effect plus the product of the idiosyncratic errors plus two terms which interact the individual effect with idiosyncratic errors in various time periods. Now, under random effects 1, or the random effects 1 assumption, specifically our strict exogeneity assumption, the latitude terms are 0. And the first part here is just the variance of the individual effect. Now lastly, let me change the color. Lastly, this term here depends on whether or not S and T are the same. If they're the same, we get the variance of the idiosyncratic error. And if they're different, we get 0 due to the serial or uncorrelatedness. So that's the structure of the composite error variance. Now, we may write this in a more convenient manner, or notationally more convenient manner, as the sum of a scalar matrix, that is the identity times the variance of the idiosyncratic error, plus this term, which is just short for a matrix or T by T matrix of these filled with these individual effect variances. We say that the composite error variance omega, when it satisfies this assumption, the composite error variance has a random effect structure, or RE structure for short. And whenever we encounter matrices that have this type of structure, or when we enforce this type of structure, we'll call those matrices, or we'll say that those matrices have an RE structure as well, or simply that they're RE structured. Let's proceed to talking about the definition of the random effects estimator. Now, since the composite error variance matrix is unknown to us, or the composite error matrix is unknown to us because in general the individual effect variance as well as the idiosyncratic error variance are unknown to us. Hence we cannot calculate omega in practice. But suppose now, at least for the moment, that we were granted consistent estimators of these variance components. That is, we were given estimators sigma square u hat and sigma c square hat. Then, as suggested by the random effects form of the composite error variance, we can construct an estimator, call it omega hat, mimicking the form by simply substituting these variance component unknowns with consistent estimators. In that case, Slutsky's theorem implies that this variance estimator is consistent for omega in the sense that it converges in probability to the right term, coordinate by coordinate. Now, given such two consistent estimators, feasible GLS is possible with this omega hat, such that we can construct the FGLS estimator. And the random effects estimator is simply feasible GLS with a random effects structured omega hat. Formulaically, the feasible GLS estimator is in our case given by this expression. Before we proceed to talk further about the structure of this estimator or what it does, let's consider a special case thereof, namely the case where the variance of the individual effect is 0. Now remember that under the second random effects assumption, the individual effect has mean 0, such that having a 0 variance means that there are in fact no individual effects. Now in this case, omega collapses to a scalar matrix, that is the identity multiplied by the idiosyncratic error variance. Since if this structure is known to us, then we could enforce it in our estimation of omega, and the random effects estimator, as repeated up here, which simply collapse to pooled or less. Now I won't go through the details at this point, but I highly encourage you to go through the different steps in the argument to see that you understand all the details. Next, we'll see that the random effects estimator amounts to something that isn't fully time demeaning, but it resembles time demeaning. For this purpose, let's introduce an additional piece of notation. So let lambda be the following constant. It is 1 minus the square root of a ratio, which is given by the idiosyncratic error variance relative to itself plus t times the individual error variance, or individual effect variance. Now one may show, using linear algebra, which I'm kind of brushing over here, one may show that the inverse of the root of the omega matrix can be written in the following form. Namely, it is proportional to a matrix, which we'll call CT, given by the t-dimensional identity, minus lambda times this PT matrix, where PT is short for 1 over the number of time periods, times a t by t matrix of ones. Here the factor of proportionality is 1 over the standard deviation of the idiosyncratic error. Now suppose for the moment that lambda is known to us, such that we may calculate omega as well as this matrix CT. That is, we could actually do generalize these squares. Then the random effect estimator can be shown to arise from estimation of the following transform system, where I've multiplied our previous equation system consisting of t equations with this t by t matrix CT. Now the purpose of doing this transformation is to get new errors which have desirable properties, and one may show that the resulting errors, which are here denoted by this boldface v with an accent breve over, has an error variance which is scalar, and the proportionality factor is given by the variance of the idiosyncratic term. Hence this system, this transform system, has a structure which is ideal for GLS in that it will yield an efficient estimator. Now if we take this system, which is an equation system consisting of t equations, and we inspect the elements, we'll see that a least squares estimator applied to the transform system actually just amounts to pooled least squares estimation of this system, where t runs through all time periods. Hence what we're really doing is that we are transforming each variable appearing in the system by subtracting lambda times their respective time averages, as represented by this yi bar, xi bar, and vi bar. Now, of course, lambda is not known to us, so we can't implement GLS in practice, but if we have a consistent estimator available, then we could construct a consistent estimator of this CT matrix, which I'll denote CT hat, simply by substituting lambda for lambda hat, our consistent estimator. In that case, we could substitute wherever omega hat appears in our previous expression, or rather omega hat inverse appears in our previous formula for the random effects estimator. We may substitute it for the square of the CT matrix, which by symmetry is simply C hat prime, CT hat prime, CT hat. So we can express the random effects estimator in the displayed manner here. And this shows, again, by expanding on the inner expressions, one may show that this amounts to a pooled OLS estimator where we've used a transformation of the regressors given by this brev notation and of the outcomes given by this brev notation. Again, the brev notation denotes that we're subtracting lambda hat times the time average of the variable in question. So what this slide shows you is that the random effects approach to estimation amounts to subtracting a fraction of the time average. Not the full time average, but a fraction thereof, since lambda is some number between 0 and 1. For this reason, random effects is sometimes referred to as quasi-time demeaning. Quasi, since it's not fully time demeaning, but something that resembles time demeaning. Again, it might be helpful to consider a couple of special cases, or limiting cases. We've already shown that the random effects estimator amounts to pooled OLS estimation of this equation system, where lambda hat again denotes a consistent estimator of lambda, having substituted consistent estimators in the place of the variance components. Now, if lambda is close to 1, or rather its estimate is close to 1, then one may expect the random effects and fixed effects estimators to be quite close to each other. One may show from inspection of the lambda formula that if t is relatively large, then the term inside the square root should be close to 0. So the case of lambda or lambda hat being close to 1 is expected to happen for large t, that is, for relatively long panels. You may also see it from our definition of Ct as the identity minus lambda pt, such that when lambda approaches 1, Ct approaches the identity minus pt. But that's exactly, we've given that matrix a name, namely Qt, which was our time demeanor or time demeaning matrix. Which popped up in our lecture on fixed effects. Hence, when lambda is close to 1, we're almost time demeaning, so random effects and fixed effects should be rather close. At the other end of the spectrum, if lambda is close to 0, then random effects and pooled OLS should be rather close. Again, this follows from inspection of omega, which in this limiting case of a 0 individual effect variance collapses to a scalar matrix. In that case, the scalars here will cancel out in our formula, or in our GLS formula, such that GLS collapses to pooled OLS. A lambda being close to 0, or rather its estimate being close to 0, you may see that it's expected to happen when the variance of the idiosyncratic error exceeds the variance of the individual effect by much. Thus far, we've taken it as given that we have a consistent estimator of each variance component available. In practice, we need to construct such estimators. So let's proceed by discussing how you would implement random effects in practice. As mentioned, if we want a consistent estimator of lambda, it suffices to have consistent estimators of the various variance components. So let's proceed by let's look for consistent estimators of the idiosyncratic error variance as well as the individual effect variance. Actually, it's actually easier to obtain a consistent estimator first of the composite error variance as well as the individual effect variance, and then invoking the third random effects assumption, we may obtain a consistent estimator of the idiosyncratic error variance by means of subtraction. So as a first step, we'll construct a consistent estimator of the composite error variance. Now here, making use of our first two random effects assumptions, which involved both an orthogonality condition and a rank condition, we can construct a consistent estimator by an appropriate average of the pooled OLS residuals. So here I'm using the check notation, or VIT check, to denote the pooled OLS residuals. And we've done, for good measure, we've done a degrees of freedom correction. Note here that pooled OLS is in fact suitable because the orthogonality condition, that is, that the composite error is uncorrelated with the regressors, is actually satisfied under the first random effects assumption. Estimating the individual effect variance is a bit more hairy, but not too bad. Now, under the third random effects assumption, we see that everywhere off the diagonal of the composite error variance matrix is equal to sigma c squared. Hence, if we average over all of these off-diagonal terms, or rather the non-redundant terms, non-redundant due to the symmetry of a variance matrix, we'll have t times t minus 1 over 2 terms. And here I'm summing up all of these terms to see that since here I'm going over all the off-diagonal terms, at no point do I have s and t equal to each other. All I'm getting is a sum of t times t minus 1 halves of the individual effect variance. Hence, if I rearrange this expression and invoke the analogy principle, I get an estimator of this variance, which we'll call sigma c squared hat. Now, this estimator is an appropriate average over all of these terms upon replacing the expectation with an average. Also, since we don't observe the composite errors, I've replaced them by the OLS residuals, pooled OLS residuals. So this gives us our second variance estimate, namely a consistent estimator of the individual effect variance. And then we obtain a consistent estimator of the idiosyncratic error variance by subtracting these two variance estimators. Or to be specific, we construct our estimator of the individual effect variance and subtract it from our estimator of the composite error variance. Next, we'll proceed to talking about how one may establish asymptotic normality of the random effects estimator, as well as establishing that the random effects estimator is efficient under certain conditions. Here I'm only going to give a sketch for the argument of asymptotic normality, and I'll leave the details for you to look at in Wooldridge. Specifically, what I'll do here is that I'll completely ignore the estimation error in obtaining omega, which one may actually show to be asymptotically irrelevant. That is, we can ignore it for the purpose of calculation. Of course, it may not be irrelevant in practice that we've estimated omega. Now, if we know omega, then we can calculate our random effects estimator using omega. And if we substitute in our model or the linear system and rearrange, we can show that the scale difference between the random effects estimator and the parameters that we're trying to estimate can be expressed as the product of two terms. One is the inverse of an average, and the other is a scaled average of variables, random variables, which are mean zero. Again, these are mean zero under our first random effects assumption. Now, assuming also our second random effects assumption, which was a rank condition, we may therefore use our previous arguments for the running in parallel to our analysis of the fixed effects estimator, as well as our cross-section, our analysis of the all-less estimator for the linear model in the cross-section, to show that the random effects estimator is asymptotically normal. That is, it is in the limit, it is distributed according to a normal distribution with zero mean and a sandwich variance formula. Here the bread of the sandwich, or rather its inverse, is the expectation of a quadratic form in the regressors, with the middle of the quadratic form given by the inverse of the composite error variance. The meat of the variance, or the asymptotic variance, is slightly more complicated, but it goes back to but you can show that it is the variance of the summons appearing in this scaled average. Again, I'll leave it for you to fill in the details here. Now, under these two assumptions, the asymptotic variance of the random effect estimator is this sandwich formula. Takes the sandwich form from our previous slide upon dividing by the sample size n. Now, the purpose of the third random effects assumption, which we haven't used up to this point, is to simplify the asymptotic variance. So if we take the meat of the asymptotic variance, the b, and we use the law of iterated expectations, we may notice that upon conditioning on the xi's, we may pull the inner expectation all the way until we hit the vi's. Since the third random effects assumption restricts the conditional composite error variance to be exactly omega, we may write b as the expectation of xi prime, omega inverse, and omega inverse xi. Hence we can cancel these two omegas, and what we're left with is exactly a, the bread or inverse of the bread in the asymptotic variance. Now, if we further use that the square root of the inverse of omega can be written as Ct up to a proportionality factor given by the standard deviation, or rather 1 over the standard deviation of the idiosyncratic error, we get the following expression. Namely, we can write the asymptotic variance of the random effect estimator, which we've now shown is just under assumptions RE1 through 3, is A inverse over N. By substituting for the inverse of omega, we can reduce this expression, or rewrite this expression, as the following product, where we've pulled out the variance of the idiosyncratic error, and we've written the second part here as the inverse of the expectation of the product of our transformed regressors, where the transformation is given by the CT matrix. Now this latter form fits exactly into the form of the variance that appears in our analysis of the OLS estimator in the cross-section under the Gauss-Markov assumptions. And since we know the OLS estimator to be efficient in that case, we may deduce that the random effects estimator is asymptotically efficient under the present assumptions, which were the 3 random effects assumptions. Having established asymptotic normality of the random effects estimator under various conditions, we may proceed to construct consistent estimators of its asymptotic variance. That would also allow us to conduct inference, say using a Walt test. Now, using the analogy principle and our recent discovery that the asymptotic variance of the random effects estimator is A inverse over n, which we could write as, I need more space, the variance of the idiosyncratic error term and the inverse of this expected product of the transformed regressors, the whole thing divided by n. We may invoke the analogy principle and replace unknowns with consistent estimators. So here I've replaced, in order to obtain a consistent estimator of the asymptotic variance of the random effects estimator, under assumptions RE1 through 3, I've replaced CT with a consistent estimator, say CT hat, and the expectation with an average, and I've replaced the variance of the idiosyncratic error with a consistent estimator. Of course, this estimator of the asymptotic variance of the random effects estimator is only a good idea, it's only a consistent estimator, under all 3 random effects assumptions. Hence, if the 3rd random effects assumption is in doubt, then we should proceed with a robust type of variance estimator. And the displayed expression here does exactly that. It goes back to our initial asymptotic variance expression, the random effects estimator, which holds under the first 2 random effects assumptions alone, and replaces both A and B with consistent estimators and cancels out any redundant ends. Now, here in constructing these consistent estimators or variance estimators, again, this V hat or boldface V hat is now given by the random effects residual. This additional need for the random effects residuals arises from our need to estimate the matrix B. Now for the remainder of this talk, we'll talk about the Hausman test. So the idea of the Hausman test is to devise a method for comparing the random and fixed effects estimators. Now note here that if we invoke all of the random effects assumptions, as well as a rank condition for the fixed effects estimator, or the fixed effects approach, then both the random and fixed estimators are consistent, while the random effects estimator, as just illustrated, is asymptotically efficient. However, if the individual effect, Ci, correlates with any of the regressors in any time period, that is, implying that the second part of the first random effects assumption fails, then the fixed effects estimator remains consistent, but the random effects estimator is not. It therefore seems reasonable that we should be able to test this assumption, the second part of the first random effects assumption, through a comparison of the two estimators, that is, by contrasting the fixed and random effects estimators, and seeing if they are significantly different from each other. If that's the case, then one way of construing or interpreting this conclusion is as evidence against this part of the random effects assumptions. So that's the idea of the Hausman test. How would you actually construct a test statistic? The Hausman test statistic formalizes the discussion of our discussion on the previous slide by constructing a quadratic form in the random and fixed effects estimators. That is, we calculate their difference and then weight their difference using a weighting matrix. For the Hausman test statistic, our weighting matrix will be the difference in asymptotic variances, or specifically the difference in our estimates of the asymptotic variances. Now, this idea comes from our previous discussion, which showed that the random effects estimator, under all the random effects assumptions, the random effects estimator was not only consistent but in fact efficient, so it should have a smaller variance than the fixed effects estimator. Hence, the term here in squared brackets should be a positive or positive definite matrix. One may formalize this intuition and show that this matrix in squared brackets is in fact positive definite, such that it has a legitimate interpretation as a weighting matrix. Now, the null hypothesis, and the hypothesis that the Hausman test is actually designed to test, is that all of the random effects assumptions and all of the fixed effects assumptions hold jointly. If that's the case, then under the null hypothesis, the Hausman test statistic converges in distribution to a chi-square random variable with k degrees of freedom. From this observation, we may use critical values from a chi-square table in order to construct a test of the null hypothesis. If we get an unreasonably large value of the test statistic, that is, it exceeds our critical value, then we should reject the null hypothesis. And in that case, it may be reasonable to reject the second part of the first random effects assumption, which was an uncorrelatedness assumption, that is, stating that the individual effect was uncorrelated with the regressors. Of course, a rejection could also be interpreted in other ways, but this is the idea of the Hausman test statistic. Before ending this talk, let me just discuss a possible pitfalls in implementing the Hausman test. Note here that since we're contrasting random effects with the fixed effects estimator, only coefficients on time-varying regressors can be contrasted. This goes back to our discussion of the fixed effect estimator in a previous lecture, where we showed that for variables which have no within individual variation across time, we cannot construct a fixed effect estimator. So strictly speaking, the k appearing in this chi-square random variable should be the number of time-varying regressors. A nice feature of this test statistic is that one may use the usual asymptotic variance estimates, but one should invoke some care in constructing these asymptotic variance estimates. Specifically, it's generally recommended that we use the same estimate of the idiosyncratic error variance in constructing both of the asymptotic variances in the quadratic form. The reason for using the same estimate is that otherwise, in practice, the variance difference may be negative. Lastly, if in a particular application we're worried about the correlation between the individual effect and a particular regressor, say xj, then we can actually use a simpler form of the Hausman test. Namely, instead of using a quadratic form, we can use a t-statistic form of the Hausman test, where we extract the relevant coordinates of the estimators or estimates and their standard errors. Under the null hypothesis, this simpler form or coordinate form of the Hausman test, or the Hausman test statistic, rather, converges in distribution to a standard normal, and we may therefore use as critical values the relevant quantiles from the normal distribution instead.